Hello everyone, this is Sangeeta and you are watching Chemistry Ke Basic Funding. In this video, we will be discussing about the different chemical reactions of the carboxylic acid. So let's get started. If we talk about the chemical reactions that may involve either the cleavage of the oxygen and hydrogen bond, or we can say the cleavage of carbon and oxygen bond, and there is possibility also that the complete carboxyl group undergo the chemical reaction or any kind of change that we will discussing. And about the another type of reaction is that the alkyl group which is present in the carboxylic or which is present attached to the carboxyl group, that also the alpha hydrogen can also get substituted by any kind of the reagent. So we will be discussing about that in this complete video. So let's get started with this. The first reactions involving the cleavage of oxygen and hydrogen bond. So in this kind of reaction, it is given by, if we just see that the carboxylic acid, when it undergoes on treatment with any kind of the metal, for example, if I just write the general one, I am just writing it, when it undergo the reaction with sodium, as this is an acid. So as we know in standard 10, you have learned that when an acid is treated with the metal, so there will be the liberation of hydrogen gas. So in this case also, what will happen when the carboxylic acid is treated with sodium? So like that of the alcohol also, you might know that when the alcohol is also treated with the sodium metal or any active metal, so that will give you the corresponding alkoxide. In case of the alcohol, that will give you the sodium alkoxide or potassium alkoxide along with the liberation of hydrogen. So if we talk about the carboxylic acid, so when it is treated with the sodium, so what kind of product will form? It will give you the sodium carboxylate along with the liberation of hydrogen gas. Okay, so it is just similar to that of the alcohols. So as the carboxylic acid are quite more acidic than the alcohols, so it can also give you the reaction with the NaOH. If it is treated with an alkali like that of the NaOH, so it can also give you the corresponding salt, that is the sodium. When it is treated with the NaOH, it will give you the sodium carboxylate along with the water molecule. Okay, so the reaction with the NaOH, it is also given by the phenols, because the phenols are quite acidic in comparison to the aliphatic alcohols. So this one reaction is also given by the carboxylic acid, because we can simply say that the carboxylic acids are quite more acidic in comparison to the phenol. So there are some other kind like that of the, it can also react, the carboxylic acid, if we say, it can also react with the weak bases like that of the Na2CO3. So on reaction, it will again give you the sodium carboxylate along with the liberation of CO2 plus H2O. So in this case, this reaction, we can say simply the reaction with the sodium carbonate or sodium hydrogen carbonate, we can use to distinguish the carboxylic acid with that of the phenol, because as the phenols are less acidic in comparison to the carboxylic acid, so they will not undergo the reaction with the sodium carbonate or bicarbonate, but the effervescence which will form in case of the carboxylic acid, that is because of the liberation of carbon dioxide, the identification test or for detecting the presence of the carboxyl group, we can use this kind of the reaction, because in this you will get a positive result. With the effervescence, you can say that okay, in a particular compound the carboxyl group is present. As we saw that the carboxylic acid undergoes the reaction with sodium hydroxide, or the weak bases like that of the sodium carbonate or bicarbonate. So it gives you the sodium salt of carboxylic acid along with the byproducts. So basically all these reactions are based on the acidic nature of the carboxylic acid. So let us discuss about the acidic nature of the carboxylic acid. So if we just say that how the carboxylic acid dissociate in water. So what will happen, as it contains the acidic proton, we can say, if it is treated with the water or in the water, it will get dissociate to give you the H3O plus ion along with that of the carboxylate ion, that is RC double bond O minus. Okay, so this carboxylate, as we know that the acidic nature of any compound, that depends on the conjugate base it will form after the removal of the proton. So in this case, more the stable this carboxylate ion, more will be its acidic nature. So in this case we can say, if we just see this carboxylate ion, after the removal of H plus ion, this carboxylate ion, this negative charge can easily delocalize in between these two oxygens. So what will be the resonating structure of this particular ion? That is, so we can simply say that the carboxylate ion which will form after the removal of H plus ion, it will be resonance stabilized. So that is why this proton, by looking at the resonating structure, we can say simply this proton is quite acidic, or it can easily, the carboxylic acid can easily remove the proton from its compound. Okay, so if we talk about the acidic nature in the water, as this reaction is in equilibrium, so if I just write the equilibrium constant for this reversible reaction, so it will be the concentration of the product by the concentration of the reactants. So it will be like this. So if I just, as we are just dissolving this, the carboxylic acid in the water, so I can just take this concentration of the water, it is in huge amount. So concentration of the water, I can just do the cross multiplication of this. So it will become so this K equilibrium multiplied by the concentration of the water is known as the Ka value. That is the acid dissociation constant. So larger the Ka value, greater will be the acidic nature. Or just like the pH value, that is the minus log of H plus ion concentration. So from the Ka value, I can just simply determine the pKa value, that is minus log of Ka. So if we see that larger the Ka value, more will be the acidic strength. Similarly, if we talk about the pKa value, so smaller the pKa value, we can simply write smaller the pKa value, greater will be the acidic strength. Just keep that in mind. that if in terms in some of the question it may be asked, arrange the following compounds in increasing order of their pKa value or in increasing order of their acidic strength, that is totally different, because smaller the pKa value, as I said, smaller the pKa value, greater will be the acidic strength. If we see the pKa value of different compounds, so that for a strong acid HCl its pKa value is -7, for the benzoic acid it is 4.19 or 4.20 around, and for the acetic acid it is 4.76, and for the phenol it is around 10, and for the ethanol it is 16. So if we see from the, if we just observe these values, so we can simply say that the strong acids having the pKa value less than 1, whose pKa value if we say is less than 1, they are considered as the strong acids, and pKa value lies in between 1 to 5, they are moderately strong acids, and if the pKa value lies in between 5 to 15, they are quite weak acidic in nature, and whose pKa value is greater than 15, so we can simply say that they are very weak acids. So in the carboxylic acid, if we just talk about the carboxylic acid, its pKa value for the acetic acids basically it is 4.76, so it is quite acidic in nature. Benzoic acid is more acidic in comparison to the acetic acid, and HCl, as you saw, that it is negative in negative, the value is in negative, so it is a quite stronger acid. So if we talk about the alcohols, this is around 16, the value of the ethanol is around 16, so it is quite weaker acid, and phenol is more acidic in comparison to that of the ethanol. Let us compare the acidic strength between phenol and carboxylic acid. As from the pKa value, we saw that the carboxylic acid is quite more acidic in comparison to the phenol, because if we saw the value, so for the carboxylic acid, for example the benzoic acid or the acetic acid, it is the value lies in between 4 to 5, whereas for the phenol it is around 10. So now let us see what is the reason, because as I said previously that the acidic strength depends on the anion which will form after the removal of H plus ion. So more the stability of the anion, more will be the acidic strength. So if we see the after the removal, if we just talk about the resonating structure, because more the resonating structure, that also we know that more the resonating structure, more will be the stability of a particular ion or the anion in this case. So if we just see the carboxylic acid, after the removal of H plus ion, it will give you the carboxylate ion. So that is resonance stabilized, so it will give you two resonating structure. And if we see the acidic strength, or if we see the after the removal of the H plus ion in case of the phenol, so that will give you basically the phenoxide ion obviously, so that is also resonance stabilized because it is attached to the benzene ring, so it will give you the 4-or, and in the next last resonating structure, that on the transfer of the delocalization of the electron, that will give you the first one structure again. So that is basically it will give you 4 resonating structure. So if we say, because अब तुम पूछोगे कि मैम पहले आपने कहा कि जितना ज़्यादा रेजोनेटिंग स्ट्रक्चर ज़्यादा स्टेबल होगा, एज ये तो फैक्ट है कि जो रेजोनेटिंग स्ट्रक्चर, और बोल सकते हैं जिस कंपाउंड का रेजोनेटिंग स्ट्रक्चर जितना ज़्यादा स्टेबल होगा या जितना ज़्यादा इलेक्ट्रॉन डीलोकलाइजेशन उसमें होगा, दैट विल बी मोर स्टेबल, दैट मीन्स मोर द रेजोनेटिंग स्ट्रक्चर, मोर विल बी द स्टेबिलिटी ऑफ दैट आयन. अच्छा, इस केस में तो तुम्हारा क्या हो रहा है, कार्बोक्सिलिक एसिड के केस में 2 रेजोनेटिंग स्ट्रक्चर्स फॉर्मेशन हो रहे हैं कार्बोक्सिलेट आयन के थ्रू, और वी कैन से बाय द कार्बोक्सिलेट आयन. बट इन केस ऑफ द phenol, the phenoxide ion, it is giving you 4 resonating structures of the phenoxide ion. So phenoxide ion के resonating structure ज़्यादा है, तो तुम बोल सकते हो कि मैम phenoxide ion तो ज़्यादा stable होना चाहिए in comparison to the carboxylate ion. So उस केस में acidic strength की अगर हम बात करें, तो acidic strength तुम्हारा क्या होगा, phenol का ज़्यादा होना चाहिए in comparison to the carboxylic acid. But एक बहुत बड़ा बट है इसमें. सी, if you observe the negative d, or we can say the negative charge, or the electrons are delocalizing in between the two oxygen, that means in between the two more electronegative atoms, whereas in case of the phenoxide, in only one of the resonating or the canonical structure, it bears, the oxygen bears the negative charge, and rest of the resonating structure, if you see, बाकी जितने भी रेजोनेटिंग स्ट्रक्चर हैं उसमें नेगेटिव चार्ज किसके ऊपर है, कार्बन के ऊपर, विच इज लेस इलेक्ट्रोनेगेटिव इन कंपैरिजन टू द ऑक्सीजन एटम. सो in this case, that one factor कि more the resonating structure, more will be the stability of the ion. So उसे अगर हम relate करें, so more will be its acidic strength, but the delocalization of the negative charge in case of the carboxylic acid, as the delocalization of the negative charge is in between the more electronegative atoms, that is it is in between the oxygen atoms. So that is why the acidic strength, this particular carboxylate ion which will form, that will be quite more stable in comparison to the phenoxide, or if we just say the acidic strength of, that is why this is the main reason the acidic strength of the carboxylic acid is quite more in comparison to the phenol. Okay, so if we talk about, हमने देख लिया, ओके, एसिडिक स्ट्रेंथ किसके ऊपर डिपेंड करता है, रेजोनेटिंग स्ट्रक्चर के ऊपर. जो नेगेटिव चार्ज डीलोकलाइजेशन होना चाहिए, अगर वो ज़्यादा इलेक्ट्रोनेगेटिव एटम के ऊपर हो रहा है, सो दैट विल बी क्वाइट मोर स्टेबल. ओके, सो नाउ लेट अस डिस्कस अबाउट द इफेक्ट ऑफ सब्स्टिट्यूएंट. ये तो हमने बात कर लिया सिंपल कार्बोक्सिलिक एसिड के केस में. तो यहाँ पे अल्काइल ग्रुप भी हो सकता है, राइल ग्रुप भी हो सकता है. दैट मीन्स फिनॉल से कार्बोक्सिलिक एसिड ज़्यादा एसिडिक होता है. You can also relate that with the phenol does not undergo the reaction with, it will not give you the carbon dioxide on reaction with the sodium hydrogen carbonate or sodium carbonate, which are weaker bases. Okay, weaker base के साथ phenol तुम्हारा reaction नहीं करता है, but the carboxylic acid, it can undergo the reaction with the sodium carbonate and sodium or the sodium bicarbonate. मतलब weak bases के साथ वो तुम्हारा easily react कर सकता है with the liberation, or we can say it will give you the carbon dioxide. Carbon dioxide को हम ऑब्जर्व कैसे करते हैं, ड्यूरिंग द रिएक्शन देयर विल बी एफरवेसेंस इन द रिएक्शन मिक्सचर. सो वी कैन से ओके दैट द कार्बन डाइऑक्साइड इज फॉर्मिंग, or the carbon dioxide is formed as a byproduct, we can say. Okay, so now let us discuss about the effect of substituent. If in the carboxylic acid के केस में ही अगर carboxylic acid में कोई substituent लगा है, whether it is electron withdrawing or donating, उसका क्या effect पड़ता है तुम्हारे acidic strength के ऊपर. So let us just see that. So as we all know that the electron donating group decreases the acidic strength, whereas electron withdrawing group increases the acidic strength. How? So if any electron withdrawing group is attached to the carboxylic acid, so after the removal of the H plus ion from the carboxylic acid, the carboxylate ion, it will stabilize this negative charge because it is electron withdrawing group. So it will drag the electron density, or we can say it will attract the electron density towards itself, that is it will stabilize the negative charge. Whereas if we talk about the electron donating group, if it is attached to the carboxylic acid, so this will destabilize this, the electron donating group will destabilize the negative charge, बिकॉज पहले ही ऑक्सीजन के पास नेगेटिव चार्ज है. सो इलेक्ट्रॉन डोनेटिंग ग्रुप क्या करेगा, और इलेक्ट्रॉन डेंसिटी प्रोवाइड करेगा, दैट विल डीस्टेबलाइज दिस एनायन विच विल फॉर्म. सो वी कैन से द इलेक्ट्रॉन विड्रॉइंग ग्रुप हेल्प्स और इट इंक्रीजेज द एसिडिक स्ट्रेंथ, whereas the electron donating group generally or basically decreases the acidic strength. So the presence of electron withdrawing group will obviously, if I just say with then, let us just take some of the example. So in this case, in some of the cases electron withdrawing group will get attached, and in some of the cases there is electron donating group. So yes, simple one I am just taking. Okay, in between these two compounds, you can simply say that the acidic strength of this compound is quite greater. Yes or no? That means the 2-fluoroethanoic acid is more acidic in comparison to the propanoic acid. Yes or no? Because here one electron withdrawing group is attached, but in this case if we just say that this one is electron donating or no group is attached, so it is quite less acidic in comparison to the fluoroethanoic acid. Okay, all of you? So now let us just see in case of the benzoic acid how the effect of the substituent changes the acidic strength, or how it affects the acidic strength of the benzoic acid. So this is about the aliphatic carboxylic acid. So ये तो simple ही है, तुम बता सकते हो कि हाँ electron withdrawing group. That also depends कि तुम्हारा जो electron withdrawing group present है वो तुम्हारे कार्बोक्सिल ग्रुप के कितने नजदीक प्रेजेंट है. इफ इट इज क्वाइट अपार्ट फ्रॉम दैट ऑफ द कार्बोक्सिल ग्रुप, सो उस केस में भी तुम्हारा एसिडिक स्ट्रेंथ डिक्रीज करेगा. डिस्टेंस देखते हैं हम कितना है इलेक्ट्रॉन विड्रॉइंग ग्रुप का या इलेक्ट्रॉन डोनेटिंग ग्रुप का एसिडिक स्ट्रेंथ डिटरमाइन करने के लिए. अगर जितना ज्यादा पास तुम्हारा इलेक्ट्रॉन विड्रॉइंग ग्रुप प्रेजेंट होगा टू द कार्बोक्सिल ग्रुप, एसिडिक स्ट्रेंथ उतना ही ज्यादा होगा इन कंपैरिजन टू अनदर कंपाउंड जिस केस में तुम्हारा इलेक्ट्रॉन विड्रॉइंग ग्रुप कार्बोक्सिल ग्रुप से ज्यादा दूर में प्रेजेंट होगा इफ इट इज अटैच्ड टू quite far apart from that of the carboxyl group. Okay, so now let us just see the acidic strength of the substituent or the isomers of the benzoic acid. If I just take, I am just writing it the simple one. Okay, so as I said, the presence of electron withdrawing group will increase the acidic strength, whereas electron donating group will, the presence of electron donating group will decrease the acidic strength. So now if we talk about the different isomers, okay, ऑर्थो पे, मेटा पे या पैरा पे तुम्हारा अगर इलेक्ट्रॉन विड्रॉइंग ग्रुप प्रेजेंट है तो उसका द एसिडिक स्ट्रेंथ तुम बोल सकते हो सिंपली कि मैम उसका एसिडिक स्ट्रेंथ ज़्यादा ही होगा. अगर इलेक्ट्रॉन डोनेटिंग ग्रुप है इन कंपेरिजन टू द बेंजोइक एसिड, और अगर इलेक्ट्रॉन डोनेटिंग ग्रुप प्रेजेंट है, सो यू कैन जस्ट सिंपली से कि मैम उसका एसिडिक स्ट्रेंथ तो ऑब्वियसली बिकॉज इलेक्ट्रॉन डोनेटिंग ग्रुप अगर प्रेजेंट है इन द बेंजोइक एसिड तो उसका एसिडिक स्ट्रेंथ बेंजोइक एसिड से कम होगा. बट there is an exception that is known as the ortho effect. वो क्या होता है? Let us just see that in the ortho effect actually the compound or the substituent which is present at the ortho position of the benzoic acid. So now let us discuss about the ortho effect, how it increases the acidic strength. See, yes, if I just draw the benzoic acid, so in the ortho position, whatever group, it may be electron donating group or electron withdrawing group, whatever group is attached in the ortho position to the carboxyl group, that will always increase the acidic strength. Just keep that in mind. The presence of either the electron withdrawing or donating, irrespective of its type, whether it is electron withdrawing or donating group, it will always increase the acidic strength. Why? See, that is because of the steric hindrance, or we can say steric inhibition of resonance. See, if I just write in this case, this carbon atom is sp2 hybridized because it is in the benzene ring, it is sp2 hybridized. So the hybridization, as it is sp2 hybridized, it is trigonal planar. So that means this particular benzene ring or this carboxyl group lies in the same plane. Okay. So what will happen if any substituent is present at the ortho position? So what it will do, it will sterically inhibit to the resonance, because अगर बेंजीन रिंग यहाँ पे प्रेजेंट है तो तुम्हारा बैक डोनेशन करके भी इनडायरेक्टली वो तुम्हारा क्या कर सकता है, एज द बेंजीन रिंग कंटेन द इलेक्ट्रॉन डेंसिटी, हाई इलेक्ट्रॉन डेंसिटी इन इट, सो बैक डोनेशन और बाय द डीलोकलाइजेशन ऑफ द पाई इलेक्ट्रॉन्स इट कैन गिव टू द कार्बोक्सिलिक एसिड. अच्छा, कार्बोक्सिलिक एसिड में अगर तुम्हारा प्रेजेंट है बेंजीन रिंग, तुम्हारा कार्बोक्सिलिक एसिड की तरफ इलेक्ट्रॉन ट्रांसफर या पाई बॉन्ड और पाई इलेक्ट्रॉन डीलोकलाइजेशन इजीली कर सकता है. अच्छा, उस केस में क्या होगा, उसे अगर तुम्हारा इलेक्ट्रॉन तुम्हारे बेंजीन रिंग की तरफ से मिल रहा है तो एसिडिक स्ट्रेंथ ऑब्वियसली कम हो जाएगा. इन कंपेरिजन कार्बोक्सिल ग्रुप में भी तुम्हारा रेजोनेंस हो रहा है, दैट इज अनदर थिंग, बट यहाँ पे बाय द बैक डीलोकलाइजेशन ऑफ द पाई इलेक्ट्रॉन्स there is, it will destabilize the carboxylate ion which will form, that means the benzoate ion. but अगर तुम्हारा प्रेजेंट है कोई भी फंक्शनल ग्रुप या बोल सकते हैं कोई भी सब्स्टिट्यूएंट इन द ऑर्थो पोजीशन, तो ये जो बैक पाई डीलोकलाइजेशन, पाई इलेक्ट्रॉन डीलोकलाइजेशन होता है, दैट विल नॉट टेक्स प्लेस बिकॉज दिस वन इज प्लेनर. एक प्लेन में तुम्हारे कार्बोक्सिल ग्रुप और बेंजीन रिंग प्रेजेंट है, बट बिकॉज ऑफ द प्रेजेंस ऑफ द दिस पर्टिकुलर सब्स्टिट्यूएंट एट द ऑर्थो पोजीशन, it will just push the electron away, or we can say it will just push this carboxyl bond out of the plane. That means ये सिर्फ प्लेन में ना रह के, because of the presence of this substituent, ये एक प्लेन में ना रह के तुम्हारा क्या हो जाएगा, डिफरेंट, मतलब आउट ऑफ द प्लेन, इट विल गो आउट ऑफ द प्लेन. सो इन दैट केस ओनली जो बैक पाई डीलोकलाइजेशन और पाई इलेक्ट्रॉन डीलोकलाइजेशन होता था वो नहीं होगा. इस केस में सिर्फ तुम्हारा आफ्टर द रिमूवल ऑफ द H प्लस आयन द डीलोकलाइजेशन विल टेक्स प्लेस इन द कार्बोक्सिल ग्रुप ओनली. दिस इज द मेन कॉज, इट इंक्रीजेज द एसिडिक स्ट्रेंथ. तो तुम्हारा यहाँ पे इलेक्ट्रॉन विड्रॉइंग ग्रुप प्रेजेंट हो या इलेक्ट्रॉन डोनेटिंग ग्रुप प्रेजेंट हो, कोई फर्क नहीं पड़ता. सिर्फ तुम्हारा बेसिक चीज होना चाहिए कि जो सब्स्टिट्यूएंट प्रेजेंट है वो तुम्हारा क्या करेगा, दैट इज नोन एज द SIR, दैट इज स्टेरिक inhibition to resonance. That is known as the steric inhibition to resonance, that is SIR effect. Okay, so this increases, this is the main reason for the presence of the substituent at the ortho position increases the acidic strength irrespective of the electron donating or electron withdrawing group. Okay, so if we just see some of the series, or in the sense if we just see the pK value of some of the compounds, so it is basically, if I just take the toluic acid along with the benzoic acid, so this one is orthotoluic acid, then this is the benzoic acid. If I just write this one is metatoluic acid, and here this one is the paratoluic acid. So if I just see the pK value, or write the pK value for the orthotoluic acid, it is around 3.9. For the benzoic acid, it is around, as we just saw, 4.19 or 20 you can say. And for the metatoluic acid, it is around 4.3, and for the para it is around 4.4. So acidic strength, if we just see, so acidic strength of the orthotoluic acid is quite greater, it is quite greater than that of the benzoic acid, irrespective, as I said, because of the ortho effect, irrespective of the electron withdrawing or the donating group, it increases the acidic strength. Okay, so just keep that in mind. Then after हमारे पैरा पोजीशन पे प्रेजेंट है, अगर कोई भी पोजीशन पे मेटा या पैरा पोजीशन पे प्रेजेंट है, दैट रिलेट्स और वी कैन से दैट डिपेंड्स ऑन द प्लस आई इफेक्ट और द प्लस आर इफेक्ट towards the or in the benzoic acid. So the basic thing is that द प्रेजेंस ऑफ ऑर्थो को, इस चीज़ को हमेशा याद रखना, बेसिक थिंग यही है कि ऑर्थो पोजीशन पे, दैट इज बिकॉज ऑफ द ऑर्थो इफेक्ट, ऑर्थो पोजीशन पे अगर कोई भी सब्सटीट्यूएंट लगा हुआ है तो आंख बंद करके उसका एसिडिक स्ट्रेंथ ज़्यादा ही होगा इन कंपेरिजन टू दैट ऑफ द बेंजोइक एसिड. तो उस केस में नहीं सोचना है कि वेदर इलेक्ट्रॉन विड्रॉइंग ग्रुप लगा है, इलेक्ट्रॉन डोनेटिंग ग्रुप लगा है. यू कैन जस्ट सिंपली से दैट ओके, ऑर्थो पोजीशन पे कोई भी सब्सटीट्यूएंट लगा है, दैट विल ऑलवेज इंक्रीज द एसिडिक स्ट्रेंथ ऑफ द benzoic acid or the substituent acidic strength of that particular compound. Okay, so now let us discuss, this is all about the acidic strength of the compounds or the reactivity in which that involves the cleavage of the oxygen and hydrogen bond. So in the reaction which involves the cleavage of the carbon and oxygen bond, so that contains when the carboxylic acid is treated with the mineral acid like that of the H2SO4 or P2O5, so it will give you the corresponding anhydride. So let me just write a simple, the general reaction. So when it is heated with any mineral acid like that of the H2SO4, or if I just heat that with P2O5, so what will happen? There will be the removal of water molecule and it will give you the corresponding anhydride. So basically you will get the corresponding anhydride when the carboxylic acid is treated with the P2O5 or any mineral acid. So that means basically dehydration will take place and you will get the corresponding anhydride. So you must have known about this, that when in the esterification reaction, when the alcohol is treated with the carboxylic acid, there is also the cleavage of carbon and the oxygen bond. So let us just see that particular reaction also. This one is for the formation of anhydride, that means in the dehydration of the carboxylic acid you will get the corresponding anhydride. So now let us just see that in case of the esterification reaction, that means in the formation of the ester, what kind of reaction and what is the mechanism of that particular reaction, how the carbon and the oxygen bond cleave. So let us just see that, that is when any alcohol is treated with the carboxylic acid in presence of an acid, or we can say in acidic medium, so that will give you the corresponding ester. Okay, along with that of the water. Okay, so now let us just see how because this particular the H plus ion or in the acidic medium which we are taking, that will act as a catalyst. Okay, and this one is also reversible reaction. If we just do the hydrolysis of the ester, that will again give you the alcohol and the corresponding carboxylic acid. So now let us see the mechanism, how actually the reaction carried out, or we can say actually the reaction takes place to give you the ester, and how the cleavage of carbon and oxygen bond takes place. So let us just see that. So first, as the reaction takes place in presence of an acid, that will act as a catalyst. So first, what will happen if I just write the general reaction? So see, as in presence of an acid, the reaction is taking place. So what will happen? The oxygen contain lone pair of electron, so that will attack the H plus ion. So if I just write this one, so it will be the protonated carboxylic acid will form. Yes or no? As the positive charge on the oxygen is not very much stable, we can say. So what will happen? Then the alcohol, which again contain the oxygen in it, that will act as a nucleophile. So it will attack to this carbon, as in between the carbon and the oxygen. The carbon is the electrophilic center, because अगर तुम्हारा ऑक्सीजन के ऊपर पॉजिटिव चार्ज आया तो वो क्या करेगा, कार्बन और ऑक्सीजन के बॉन्ड में जो डबल पाई बॉन्ड है उसका इलेक्ट्रॉन्स अपनी तरफ लेगा. सो इन दैट केस द अल्कोहल विल अटैक द इलेक्ट्रोफिलिक सेंटर, दैट इज द कार्बन, एंड देयर इज electron transfer. Okay, so now if I just write this one, what kind of species will form? That is, okay, O with, as it is giving for the bond formation, oxygen is giving its lone pair of electron, so there will be a positive charge on the oxygen. Okay, so now what will happen? There will be a proton transfer. Okay, that means this proton, obviously it will also try to become neutral, as a positive charge is on the more electronegative atom. It is also not quite stable. So what will happen? There will be the proton transfer. So how the proton will get transfer? That means this will attack this proton and make the O plus ion as the neutral oxygen or the stable oxygen. So if I just write the next species which will form, that is, as it is giving for the bond formation, it is just accepting or just accepting the proton. So obviously there will be a positive charge on this oxygen along with 2 hydrogen, and it is attached to the carbon, and here there will be, so if I just write the R dash so that you will be able to understand. Okay, so this will form, all of you can see, so this will form. Then afterwards what will happen? There will be the removal of water molecule. That means this particular, there is removal of the water molecule. That means this will give you this particular electron. The oxygen will give the electron. It will help it out for the removal of water molecule. So in the next step there will be the loss of water with what we will get, that is, okay, let me just write it here, R dash C, one second, C double bond oxygen with a positive charge in it, as it is giving its lone pair of electron, and there will be OR. Okay, this compound will form. Then after that, let us just see, as there will be a loss of proton in the last step. So in the loss of proton, after the removal of this proton, it will get stabilized and you will get the corresponding ester. Okay, all of you. So that will be the protonated ester which will form. So after the removal of this proton, the H plus ion, you will get the corresponding ester. Okay, so this is the mechanism how the esterification or the reaction of the carboxylic acid with an alcohol in presence of an acid which is used as a catalyst takes place. So another type of reaction we will see which involves the cleavage of the carbon and oxygen is the reaction. So now let us see another set of reactions. which comes under the cleavage of the carbon and oxygen bond. So like that of the alcohol, when the alcohol was treated with that of the PCl3, PCl5 or SOCl2, it was giving you the alkyl halide along with the byproducts. Similarly, in similar way, the carboxylic acid will also react with these kind of the compounds or with these compounds to give you the acid corresponding acid chloride. So let me just write the reaction. A general one, when the carboxylic acid is treated with PCl3, say, so it will give you the corresponding acid chloride along with H3PO3. The byproduct will remain the same, that of the alcohol. So basically this will change, that is, instead of the alkyl halide, when the carboxylic acid is treated with the PCl3, it will give you the corresponding acid chloride. So if I just write one more reaction, that is with the SOCl2, thionyl chloride, so it will give you again the acid chloride along with SO2 and HCl. So basically for the preparation of the acid chloride or for the formation of the acid chloride, this method is used because the byproduct which will form, again, as these are the easily escapable gases, so you will get the pure or in a good percentage of yield of this acid chloride. So this is generally used, this method is used for the preparation of the acid chloride. Okay. So now let us see what will happen when the carboxylic acid is treated with ammonia. So next, another reaction which also comes under, there will be the cleavage of carbon and oxygen bond. So let us just see that. When the carboxylic acid is treated with ammonia, so first it will give you the ammonium salt of the carboxylic acid, which on further heating will give you the acid amide, or simply the amide you can say. So let me just write one reaction. The general one, if I am just writing, then we will see with one example or a particular compound we will just take when it is treated with the ammonia. So first it will give you the ammonium carboxylate, the salt, ammonium salt of the carboxylic acid will form, that is the ammonium carboxylate, which on further heating there will be the removal of water molecule, the dehydration will take place in this salt, so you will get the corresponding acid amide. Okay, so in this case you will get the corresponding acid amide. For example, if I just write instead of the R any alkyl group, for example if I am just taking the CH3, the ethanoic acid on reaction with the NH3, it will give you the ammonium ethanoate first, which on further heating it will give you the acetamide. Okay, or ethanamide you can say. So it will give you the amide. These are all, as they are derived from the carboxylic acid, like that of the acid chloride in the previous case we saw. This is also, the amide is also an acid derivative, as they are derived from the carboxylic acid. Okay, so you might have heard in the amines that Gabriel Thalamide reaction, because in the amines for the preparation of the primary amine, generally the Gabriel Thalamide reaction is also one of the method. So in that case the thalamide, so now let us see how actually the thalamide we can get from another starting, or how we can get the thalamide. So let us just see that this actually comes from the phthalic acid, thalamide which will form, that is actually from the phthalic acid. So phthalic acid is basically when two carboxylic acids, or we can say the two carboxyl groups are present at the ortho position of the benzene ring, they are known as the, that particular compound is known as the phthalic acid. So when it is treated with the ammonia, so what will happen, as two carboxyl groups are there, so it will react with two molecules of the ammonia and give you the, so I can just simply write it CO minus NH4 plus here also. it will give you the basically the ammonium phthalate. The salt of ammonium salt of the carboxylate, that is the phthalic acid is here. So it is known as the ammonium phthalate, which on further heating, if you just strongly heat that, so it will give you the phthalimide. Okay, as the amide will form, there will be the removal of water molecules, as yes, 2 water molecules will get removed, so you will get the phthalimide, that is C double bond O NH2, here also C double bond O NH2. Okay, which on further heating, if we just strongly heat that is on strong heating, strongly if we just heat this one, so there will be removal of ammonia molecule, that is, so if I just write it, not okay, so there will be removal of, let me just write it like this way. Okay, one second. Okay, so in this case there will be removal of an ammonia molecule and you will get the phthalimide, that is N here H, yes, this one. So this one is the phthalimide, this particular compound which will form, that is known as phthalimide. There is a difference because Al after that I is there, but here as the amide is forming, so that is known as the phthalimide instead of phthalimide. So after strong heating, so it will give you, there will be a removal of the ammonia molecule and you will get the corresponding, that is the phthalimide. So in the Gabriel synthesis, we use generally this particular phthalimide for the formation of primary amine, isn't it? Okay, so now let us just see, these are the different reactions, set of reactions which includes or which involve the cleavage of the carbon and oxygen bond. So now let us see the reaction which involve the complete carboxyl group. Okay, now we will see the next set of reactions which involve the complete carboxyl group in it. So basically, as we know that the carboxylic acid on reduction, it will give you the primary alcohol in presence of, or we can say on reaction with the strong reducing agent like that of the LiAlH4, it will give you the corresponding primary alcohol. So it will give you RCH2OH. So similarly, like that of the other reducing agents are also there. So the diborane, if we just see that the diborane is other reducing agent which can also, that is B2H6 in presence of the tetrahydrofurane, a solvent. So that will also reduce the carboxylic acid to give you the corresponding primary alcohol. Okay, so in the reducing agent, if we just see the different reducing agent, there are some reducing agents like that of, for example, the B2H6, that is the diborane. So in presence of the tetrahydrofuran as a solvent, this will form a complex, so which will reduce the carboxylic acid to the corresponding alcohol. But this B2H6 complex, the diborane, is not able to reduce the ester group, the nitro group or the halo group from the compound. So we can use this particular reagent, the reducing agent, for selective reduction. So if I just write one reaction, for example, yes, the benzoic acid with, or we can say the para-nitrobenzoic acid. If I just want to prepare it as the benzyl alcohol, if I just want to reduce this just carboxylic acid, not the nitro group, so I can just simply use this particular compound or this particular reagent, so that it will give you the NO2 will remain as it is, because the B2H6, the diborane, is not able to use the nitro group, so it will give you the benzyl alcohol, the substituted benzyl alcohol. So this can be used. Similarly, if I just want to, I can just simply take the LiAlH4 for the formation. Okay, along with the LiAlH4, at the end there will be the hydrolysis. Okay, so in presence of, if I just take the LiAlH4, as it is able to reduce the carboxylic acid to give you the primary alcohol, but the multiple bonds, or we can say the alkenes or alkynes, generally do not get affected by the hydride reducing agents like that of the LiAlH4, NaBH4. That means the hydride reducing agent does not affect the presence of multiple bond in the compound, or it will not reduce the multiple bond, we can say. So if I just write the one of the reaction using the hydride reducing agent, which also contain the carboxyl group in it. So yes, if I just take, okay, so if I just treat that with LiAlH4 along with water, so it will give you, it will not affect the double bond, it will only reduce the carboxylic acid or the carboxyl group to give you the corresponding primary alcohol. So this also we can use if we want to prepare a compound, if we want to reduce only the carboxylic acid from a given compound, so we can use this LiAlH4. It will not affect, that means that particular compound also contain the multiple bond, and we don't want to affect that, or we don't want to change that multiple, change in the sense we don't want to react that, so that that particular multiple bond will not react with the reagent. So we can use the hydride reducing agent, because that will not, the alkenes or the alkynes, the multiple bond generally do not, basically the alkenes generally do not get affected by the hydride reducing agent. So we can use this one reaction. Okay, so another type of reaction, or we can say another reaction which involves the complete carboxyl group in it, the reaction with the complete carboxyl group in it, so that is known as the decarboxylation reaction. So in the decarboxylation reaction, from the name itself you can say that there will be the elimination of the carboxyl group. Yes or no? Everybody, you can say just simply by looking at the name, that is the decarboxylation reaction. So in this, what will happen? The carboxylic acid, when it is treated with the soda lime, that is a mixture of NaOH. Okay, let me just write the reaction. Okay. The NaOH and CO, that is this particular mixture of NaOH and CO is known as the soda lime. So when it is treated, the carboxylic acid is treated with the soda lime, when it is heated with the soda lime, we can say, so that there will be the removal of carbon dioxide. So what will happen? There will be the formation of a hydrocarbon along with the carbon dioxide, we can say, as Na2CO3 will form, which on further decomposition will give you the carbon dioxide. So this reaction will take place. So as the complete C double bond O and O, the carboxyl group, is getting reduced, or we can say is getting removed, so that is why this is known as the decarboxylation reaction. And one more thing, that the NaOH and CO which are present in the soda lime, so they are in the ratio of 3:1. That means 3 portions of the NaOH and 1 portion of the CaO will form the soda lime. Okay, all of you. So one more reaction is also there, in which the decarboxylation takes place, that is known as the Coarse Electrolysis. You might have learned about this in standard 11th in the preparation of the hydrocarbon. So in the coarse electrolysis, the alkali metal salt of the carboxylic acid, if I am just writing it, is treated with or is electrolyzed basically in its aqueous solution. When it is electrolyzed, that means when electricity is passed through the aqueous solution of the sodium salt or the potassium salt of the carboxylic acid, so it will give you the hydrocarbon which contain twice the number of the carbon atoms present in the alkyl group of the acid. Okay, so in this case also the decarboxylation takes place. So now let us discuss about another set of reaction, or we can say another type of reaction which contain the hydrocarbon part of the carboxylic acid, which contain the hydrocarbon. That means what kind of substitution is there in the hydrocarbon part of the carboxyl group or that particular carboxylic acid. Now let us see the substitution reactions in the hydrocarbon part of the carboxylic acids. So in this case, the first one reaction under this type is the alpha halogenation. So in this reaction, as from the name you can see the alpha halogenation. That means when the carboxylic acid, any carboxylic acid which contain the alpha hydrogen atom is treated with the chlorine or bromine in presence of the red, small amount of the red phosphorus, the alpha, at the alpha position, the chlorine or the bromine substitute the hydrogen and you will get the alpha halocarboxylic acid. So if I just write the reaction, a simple one, if I am just writing in this way, yes, as I have to show that it contains, this one is the alpha hydrogen. Okay, so when it is treated with the X2, the X can be chlorine or bromine in presence of a small amount of red phosphorus. So again on hydrolysis, it will give you, this hydrogen will get replaced by the halogen atom. So that you will get the alpha halocarboxylic acid. So as this one is the alpha carbon atom, so this one we will get the alpha halocarboxylic acid. So as the at the alpha position the substitution is taking place, so that is why it is also known as the alpha halogenation, or we can say yes, alpha halo. If I just write it, you will get the alpha halocarboxylic acid. So this one is a name reaction known as the Hell-Volhard-Zelinsky reaction, also known as the HVZ reaction, that is the Hell-Volhard-Zelinsky reaction. So X can be, we can say the Cl2 or the Br2. Okay, so in this case the hydrocarbon part is taking it will undergo the reaction or the substitution by the halogen molecule. So in presence of a small amount of the red phosphorus, that will give you the alpha halocarboxylic acid, and it is a name reaction that is known as the HVZ reaction or the Hell-Volhard-Zelinsky reaction. So if we see talk about the electrophilic substitution reaction. So as you know that in the electrophilic substitution reaction of the aromatic compounds, for example, if we just talk about the benzoic acid. So in that case, what will happen, as the carboxyl group is electron withdrawing, so by just drawing all the resonating structure, you will be able to know that it is ring deactivating and meta directing. Okay, as it is an electron withdrawing group, so from the resonance, if you just draw all the possible resonating structures of the benzoic acid, you will get to know that it actually deactivates the benzene ring, because as it is electron withdrawing, so obviously it will withdraw the electron density from the benzene ring and deactivates the ring, and also it is meta directing. So if I just write some one or two different electrophilic substitution reaction, so in that case, yes, like that of the different electrophilic substitution reaction in the aromatic compounds are like that of the halogenation, nitration, like this. Okay, so about the Friedel-Crafts reaction, but in this case one thing is there, why the benzoic acid, it will not undergo the Friedel-Crafts reaction. We will just see that. I am just writing the simple, if I just write, okay, as it is ring deactivating and meta directing, so on nitration, when it undergoes the nitration, that means concentrated HNO3 in presence of concentrated H2SO4, so the nitronium ion which will form, that will get attached at the meta position with respect to the carboxyl group. So that is, you will get the meta nitro benzoic acid as the product. Okay, so similarly if I just do the halogenation, so in that case also the halogen atom will get attached. So in this case Br2 I am just taking in presence of a catalyst, that is the Lewis acid, that is FeBr3. It will give you the meta product. Okay, so in this case you will get the meta bromobenzoic acid. Okay, so these are the different electrophilic substitutions. So now if we talk about the Friedel-Crafts alkylation or acylation, because that is also come under the electrophilic substitution of the aromatic compound, but generally the carboxylic acid or the benzoic acid do not undergo Friedel-Crafts reaction, because one thing, it is ring deactivating, and one more thing is there, as the reaction in the Friedel-Crafts alkylation or the acylation, the reaction takes place in presence of the anhydrous AlCl3, that is a Lewis acid. So actually that get bonded with the carboxyl group, that is why it will not undergo the Friedel-Crafts reaction. So basically if we just talk about the electrophilic substitution, the nitration is there, halogenation is there. Okay, in case sulfonation can also be, we can say yes, the sulfonation can also takes place. So but Friedel-Crafts, regarding the Friedel-Crafts reaction, it will not give you the Friedel-Crafts reaction, because the AlCl3 will get attached, it will get bonded to the carboxyl group, because the oxygen also contain the lone pair of electron and AlCl3 is Lewis acid, that means electron deficient, so it will get bonded to the carboxyl group and will not undergo the Friedel-Crafts reaction. This is all about the different types of the reaction of the carboxylic acid, either the alkyl or aliphatic carboxylic acid or the aromatic carboxylic acid. So that's all. Thank you.